section 4.3, we've been focusing in on logarithms and logarithmic properties. Now we're going to switch back to exponentials. This whole chapter we kind of go back and forth because they go hand in hand. So just a reminder about what an exponential equation actually is. An exponential equation is an equation that has an exponent containing a variable. So in case that wasn't clear before, let's just throw that definition in there. Alright, so one more time, an exponential equation is an equation that has an exponent containing a variable. So that's an important distinction because we have already dealt with functions that have exponents, right? In fact, when we talked about them in the last couple of chapters with polynomials and rational functions, the exponents are an important detail because they tell us the degree of the polynomials and help us understand the asymptotes in our rational functions and things like that. But in this case, this is a very different distinction because the exponent itself is the variable or the unknown and can change. Alright, let's look at our main focus, which is solving equations. So we're going to go through a checklist of things that will help us know how to solve an exponential equation. Okay, first thing to do is to rewrite the equation in the form either an exponential that equals an exponential, or an exponential that equals a number. Okay, so this is where we have both sides are exponentials, and this is where one side is an exponential and the other side is a constant. The main idea by getting it to this form is dividing out any coefficients that might be in the way of it looking like this. So maybe just make yourself a little note, because we're going to see that later, is divide out coefficients. So for example, if I had something like 3 times 2 to the x equals 12, the first thing I would need to do is I would need to divide both sides by 3 so that I would have 2 to the x equals 4. And that would be putting this in this second form with an exponential that's equal to a constant. We've gotten rid of the coefficient in front of the exponential. That's the important part of step 1. Okay, step 2. If both sides are exponentials, so we have like this first form here where we have a base to a power equals a base to a power, and the bases are the same, or we can change them to be the same base, then we are going to use the one-to-one property, which is one we've already seen, I think in section 4.1. And what that property says is that if b to the m equals a to the n and b equals a, so that our bases are the same, then we can just set the exponents equal to each other. M equals n. So we create a new equation by setting those exponents equal to each other, and then we solve. So like I said, we've already kind of seen that in section 4.1, and we will see that again today. If the bases are not the same and there's no way to make them look the same, so a and b are completely different numbers and it's not like B is a 3 and A is a 9 that could be changed to a 3. Then what we have to do is take the log of each side. So take the log of each side. And then we use the power property or the exponent property to move the exponent, which is the variable, out to the front. And that way we can divide stuff and get that variable by itself. So take the log of each side and use the power property. To rewrite the equation. So, for example, if I had something like 2 to the x equals 5, I would change that to x log 2 equals log 5. I kind of did 2 steps there in one. That's supposed to be a 5. 2 steps in one. So I took the log of each side and then I moved the exponent x out to the front, and now I can solve it by dividing both sides by log 2. So that would give me log 5 divided by log 2, which is a beautiful exact answer, or we can throw that in a calculator and get an approximate answer if we've used a log base 10 common log or a log base e natural log. And it doesn't matter which one you use, either way you'll get the same ratio instead of the same answer. If only one side has an exponential, like we have a number to a power equals just a constant, and if that exponential is equal to a negative or 0 constant, then we have no solution. Because we can't take the logarithm of a negative or 0, it's not possible to take an exponential, take a number to a power, and get a 0 or a negative answer. If only one side has an exponential, and if the exponential is equal to a positive constant, then we can do something similar to what we did in step 3, and that is we're going to take the log of each side and then we're going to rewrite with the power property. Like we did in the example, just barely, like up here, right? Or another idea is you can actually change to exponential form. I said that wrong. We can change our exponent to log form. Now, the disadvantage of doing that is that it's possible we'll get a logarithm that's not base 10 or base e, and then we wouldn't be able to approximate that with the calculator without using the change of base formula. But it's still a valid way to do the problem. So with either step 3 or step 5, take the log of each side, use the power property, and then we're going to use algebra and properties of logarithms and solve for the variable. And then with exponential equations, we don't need to check our answers because the domain of exponentials is all real numbers. Okay, let's see this in some examples.